Second order linear homogeneous ordinary differential equations. Second order because we have second derivative. Linear means we have y, y prime, y double prime, and the coefficients are just functions of independent variable. In this question, in this case, we are taking y as a function of t, and in fact these are constants. So second order linear constant coefficients, what is, and homogeneous means the right hand side, I mean there is no pure function of t, it's just 0. This is 0, that's why homogeneous. Now we want to solve these types of equations. Okay, so we can guess the type. Give me a function whose derivative, second derivative is the same. Okay, it has to be the same so that we can combine and just plus minus, this becomes 0. So the function which has same derivatives over and over is exponential type. So we assume y is a function of t equals e raised to some unknown, we don't know, let's say rt, be a solution of this equation 1. Okay, be a solution. Solution means we can plug this back here and the left hand side is equal to 0. Okay, this satisfies this equation. To plug this y into equation 1, we have y, y prime, y double prime. So we need to find y prime and y double prime. Okay, y is e raised to rt. We are just guessing. Okay, this is a solution, and later we'll find the value of r. Then y prime, derivative from chain rule, r e r t, and y double prime, r square e raised to rt. Plug these into the ODE. A y double prime, this is y double prime, a r square e r t plus b, y prime is here, so b r e r t plus c y, y we assume e raised to rt equals 0. In each term we have e raised to rt, so we can factor that out. That leaves ar squared plus br plus c equals 0. Okay, now we got a product of two things equals 0. Since exponential functions are never 0, this is never 0, that means this must be 0. This implies ar squared plus br plus c equals 0. Okay, and in fact this polynomial in R, this is degree 2 polynomial or quadratic equation in R, this characterizes the solutions of equation 1, and it is called a characteristic equation. In fact, the characteristic equation of 1, okay, called the characteristic equation of equation 1 of ODE 1. Okay, now when we solve this equation 2, which is a quadratic equation, we have three cases, and in this video I'm just gonna cover the first part. Okay, solving 2, we get three cases. The roots are real and distinct. Case 1, roots, when we find two roots, maybe r1 and r2, roots are real and distinct. As we know, the discriminant here, which is b squared minus 4ac, when that is positive, we get this case. Say r equals r1 and r2, and they are not equal, and they are both real. In that case, our solutions are given here. So e raised to rt was a solution, so r equals r1 is one solution, then e raised to r1t is a solution, and e raised to r2, another root is r2, t is another solution. That means these two are solutions of the ODE1. And note that since R1 and R2 are distinct, we cannot get second solution is not a constant multiple of first. Okay, that means these two functions are linearly independent. Okay, and when they are linearly independent, so it's a second order. Second order means we can have at most two solutions. So we have two solutions here, and they are linearly independent. That means these two solutions form a fundamental set of solutions. Okay, since these two are linearly independent, ER1T, ER2T, this set forms a fundamental set of solutions of 1. Okay, and from the principle of superposition, a linear combination of these two, so someone constant C1 times first solution plus C2 times second solution, this linear combination is also a solution, and this is called the general solution. So this is y. Now y is a function of t equals this is the general solution, or a general solution. These constants could be anything, is the general solution. And some people say is a general solution, same thing. Okay, this is how we find the solution for this type. So let me do one example. The question is solve the ODE. Is given y double prime minus 5y prime plus 6y equals 0. Okay, so we don't have to start from e raised to rt. We can if you like, but I want to start writing the characteristic equation here. Okay, so for this ordinary differential equation, the characteristic equation is a means 1, so ar squared means 1r squared plus br, b means minus 5r plus c, which is 6, equals 0. Now we can solve this for r, just factor, then that is r minus 2, r minus 3 equals 0. So we get r equals 2 and 3. That means e raised to rt means e raised to 2t is one solution, and e raised to 3t is another solution. And we can never get one solution by a constant multiple of another. So they form a fundamental set of solutions, and if we take just like any constant a or c1 plus c2 this, and that's the general solution for this. Okay, that's it. Okay, next example. If we have initial conditions given, because there are two constants, that means we should have two initial constants. In that case, we can determine c1 and c2. So another example is solve the IVP. Let's say the IVP is just y double prime minus 5y prime plus 6y0, and we got two initial conditions, y0 equals 1 and y prime at 0 equals negative 2. Okay, to solve this, first we find the general solution like last time. This is the same ODE like here, so you need to find the characteristic equation, then find the roots. Okay, we are just considering the real and distinct roots case. Then we have this general solution. So after this work, we have the solution. Okay, a couple of steps. C1 e raised to 2t plus C2 e raised to 3t. Now, using these two initial conditions, we need to determine the values of C1 and C2. Okay, look at the second initial condition. It has y prime. That means we need to find its derivative. Okay, just to apply second. Let's find the derivative. From general, 2c1 e raised to 2t plus 3c2 e raised to 3t. Okay, we found first derivative. This is not solution. This is solution when we know c1 and c2. This is just to apply second boundary, second initial condition. Y at 0 equals 1. Let's apply here. Using y at 0 equals 1. Y is 1 when t is 0. So y value, this is 1 when t is 0. So c1 e raised to 2 times 0, 0. E raised to 0, which is 1. c1 times 1, just c1, plus c2 times e raised to 0, same thing, c2. Okay, let's say this is star. And using the second initial condition, is y prime at 0 equals negative 2. So we're gonna apply here. Y prime is negative 2 when t is 0. So negative 2 equals 2c1 times e raised to 0 because t is 0. So 1. So this is just 2c1 plus 3c2. Okay. Now this is a system of linear equations in two variables, c1 and c2. Now we have a couple of methods to solve for c1 and c2. We can use elimination or substitution, or we can even graph like x plus y equals 1, 2x plus 3y equals negative 2, something like that. Okay, it's algebra 1. So let's solve. So I'm gonna eliminate. This is 2c1, c1. Let's multiply this by negative 2. That makes this negative 2, negative 2c1, negative 2c2. Then combine. Okay. Then what happens is 2c1, 2c1 cancel. I just multiply by negative 2 to cancel. 3c2 minus 2c2, just c2. And the negative 2 plus negative 2 is negative 4. So we got the value of c2. Okay, now we can plug in the first. Before I multiply by negative 2, it was just 1 equals c1 plus c2. And then c1 plus c2 is 1. Okay, and moves negative 4 over, so c1 is 5. Okay, c1 is 5, c2 is negative 4. Now we go back here and write down the final answer. So thus y is c1, which is 5 e raised to 2t, plus c2 is negative 4 e raised to 3t. Final